Okay, we are almost ready. And so this afternoon we will see optimality principle in design and control of soft robots. That is the work I have been done in my PhD in the University of Pisa under the tutoring of the professor Antonio Bicchi. And so today, since I know you are anxious to work on the demo, I will keep it short as possible, and I will present basically the results of this work, and I'll skip a little bit on the details, on the proofs, on all the calculations. So let's start. Okay, so for one who works, this video is supposed to, okay. So for one who works in robotics, it's unavoidable to make comparison between what human can do and what robots can do. In this slide, you can see the max speed that a human, let's say Usain Bolt, not an average human, but Usain can reach, that is 44.7 kilometers per hour. And the maximum jumping height from standing, that is 1.6 meters. That is like this. It's impressive. And a robot, also in this case, we have the state-of-the-art performance for robots, reached here by Asimov, can run at 9 kilometers per hour. Let's see something else. Here we have, if the video starts. Okay. Here we have the record, the world record of the marathon. That is 2 hours and some minutes. So it means that a human being, also in this case Wilson Kipsang, can run at more or less 20 kilometers per hour for 2 hours. And if you want to speak about the robustness of our body, a man can survive a dive from 50 meters. While, as you can see, Asimov can't survive a fall from the 3rd step of a stair. Unfortunately, this is the state of the art. Okay, so these characteristics, maximum performances, energy efficiency, and robustness, are very important, and not just in high performances in sports, but also in everyday life. For example, here you can see pictures that represent operations that today can be performed just by humans. So, up to now, no robot can do things like this one. And the robotics community feels the challenge. So, for example, in the next months, it will take place the DRC, so the DARPA Robotics Challenge competition in the US, in which humanoid robots are supposed to do tasks like open branches in walls, drive a car, climb the stairs of some steps, of some And every task has to be accomplished one after each other, and all the task, the whole competition will last 1 hour. So the robot will be completely on its own and will rely on its own power source. So it has to be efficient. It has to be. It needs high peak performance, and also it will not have any structure for preventing it to falling down. Also, in fact, it has to be robust. It is foreseen that the robot can fall down, and it is supposed not to be damaged due to a fall, and to accomplish the task. So why humans are so dexterous, are so efficient? Probably one of the reasons is in our musculoskeletal body. Our joints are actuated by muscles that allows us to perform operation in soft and strong way. So the idea is to embed impedance regulation in robots. And basically, in the literature, two were the way in which these have been done. One is active variable impedance. That means that the impedance regulation was embedded in robot by active control. The other one is intrinsic variable impedance or physical variable impedance. That means that the robot is able to physically adjust, to physically change its impedance. And this is the new generation, and something that the new generation of soft robots can do. For example, in the top of the slide, you can see the DLR hand-arm system that can hit and be heated. So that is what I meant for robustness. No way. It's impossible doing something like that with a rigid robot. And then in the bottom of the slide, you can see Patman from Boston Dynamics that has sort of intrinsic elasticity because its actuation is performed by pneumatic actuators, and the humanoid robot from by IIT common that is actuated by series elastic actuators. So the soft robotic technology seems to have a great potential. And today the technology is available. There are several laboratories around the world that are working on these ideas. And the problem now is how to manage the additional degrees of freedom that the soft robots have. Here are two of the possibly many solutions. One is transferring human skills to robots. So let human do tasks for you, and then copy the way humans changing and regulating their impedance. The other one is deriving laws in which laws that can explain how impedance has to be changed according to the tasks. by optimality principle. And the second one is the path, the idea that it has been following in the work you are going to see. Why optimal control? First, because optimal control allows to factorize the control, actually, the control design out of the equation. So that means that you can compare several systems and their performances without taking into account the control. That means that at the end of the comparison, you will not have to face the question, okay, I have this system, it works like that, but if I change the control, okay, since here the control is already optimized for the system, then you can have a, let's say, fair comparison between several systems. The other reason why we think that optimal control is important and is useful is that helps to understand basic principles, that helps to understand lessons that can be derived from the analysis of simple systems and then can be applied, the principle can be applied to several use cases. So from this point of view, we studied three main problems that are in some sense related to what we have seen before, so to peak performance, energy efficiency, and robustness. For peak performances, we studied the problem of maximizing the peak speed of a robot. From the energy efficiency point of view, we studied the problem of minimizing the energy consumption during a cyclic task. And from the robustness point of view, we studied the problem of minimizing the tracking error, in this case the force tracking error, under constraint on the maximum force that the transmission can sustain. So let's start with the max with the max speed problem. So the idea is, the objective, the goal is to maximize the effect of an impact. Like, for example, we do when we want to hammer in a nail or we want to hit something. We translated the problem from a mathematical point of view into the problem of maximizing the speed that here is named Q dot of the link side, of course, of the actuator. And the index maximization is subject to the dynamics constraint, in this case, the dynamics of the soft actuator. And, of course, here there are the initial conditions. There is a terminal constraint. So what does it mean? It means that we want to maximize the velocity of our link, but when we are at the position in which we want to hammer the nail. Okay? So, dynamics, initial conditions, and terminal constraint. That is the position of the output shaft of the link. So, first First, we studied the problem for the series elastic actuation. Why? To see if there is an optimal constant stiffness value for maximizing the speed of the peak speed of the actuator. And then we switch to the variable stiffness case in order to see if there are any advantages in changing the stiffness during the task, and above all, how the stiffness has to be changed. So now let's see the the results for the series elastic case. We studied 3 problems. In the first one, we used the position control scheme. So basically, we assumed that the position of the motor is the control variable. Here you can see the dynamics in state form of the actuator, and here U represent the position of the motor, Q that here is x1. Here you can see the definition of the state, represent the position of the link. Omega is the natural frequency of the system. And here are the control limits. So basically in this case, the control limits are limits on the position of the actuator that you can see as limits somehow on the force the actuator can generate. And then, of course, initial and terminal conditions. We derive the solution through standard methods from the optimal control theory. So basically, we write the Hamiltonian of the problem, then the constant dynamics. Through the analysis of the Hamiltonian, we can derive the fact that the optimal control is bang-bang-like, so that the control law for the position of the motor has to be maximum and minimum, and it has to switch according to the sign of lambda with 2, that is one of the costates. And then this is the switching function. Okay, this is the problem statement for the speed control case. So in this problem, we assume to control the velocity of the motor, not just not anymore the position. And the dynamics of the problem has one state more, so now the position of the motor has become one state, and its derivative, the control. And then we studied the problem in which we assume to control the acceleration of the motor. Okay, so basically what happened to the dynamic is that we need one state more again, that is the velocity of the motor, and then its derivative is the new control. Okay, so these problems are, let's say, simple enough, and we were able to derive complete analytical solutions for all these problems. Complete analytical solutions not just for the control laws, but also for deriving, for example, the formulas that gave the peak speed of the actuator. In this case, you can see that for the position control case, the maximum speed that the actuator can reach. Of course, in all the three cases, the maximum speed depends on the bound on the control. That's obvious. But the most interesting fact is that in the position case, the maximum velocity is proportional to omega. In another, since the stiffness is the thing we are looking for, is proportional to the square root of the stiffness. In the speed control case, the maximum velocity the actuator can reach is independent on the stiffness. In the acceleration control case, the maximum speed decreases if the stiffness increases. Okay, so it's strange. We are studying the same problem, and on the basis of the model we are using, we obtain three very different behavior of the solution. So we proceed and we studied the problem from a more realistic point of view. So basically we studied the acceleration control problem, but also with constraints on the speed and on the position. And so basically this plot sums up the results we obtain. The dashed blue line represents the position control case. So in the y-axis we have the maximum speed. In the x-axis the omega, the natural frequency of the system. Okay. So the dashed blue line represents the solution of the position control case. The dashed red line represents the solution of the speed control case, and the black dashed lines represent the solution of the acceleration control case. And the continuous red line represents the solution of the problem with acceleration control and constraints on velocity and position of the actuator. So basically the more realistic model we analyzed so far. And as you can see, if the natural frequency of the system is low enough, the solution of the complete problem resembles the one the position, so the solution of the position control case. So that's why basically in these cases the position constraint is what is more important for the solution, and the speed constraints and the acceleration constraints are don't play a very important role in the solution of the problem. So that's why the two problems give a very similar solution. The same happens if the natural frequency of the system becomes rather high. So in this case, the acceleration constraint plays the most important role in the solution of the problem, and that's why the two solutions, the one of the pure acceleration control case and the one of the complete case, are almost identical. And in this region, what happens is that all the constraints contribute and are active. And so all of them has to be taken into account to derive a correct solution of the problem. In a sense, the solution of the speed control case can be seen as a pure theoretical upper bound of the maximum performance that can be reached, and basically it says that a soft actuator can reach theoretically can reach a speed that is 4 times higher than the speed that can be reached by a rigid actuator with with a maximum velocity constraint. Okay, so this velocity is 4 times the upper bound of the velocity of the rigid motor. Another important result that comes out from this, from the analysis of this plot, is that there is an optimal value of the natural frequency of the system. So, in our analysis, what is important is that there is an optimal value of the stiffness of the actuator that maximize the performance, the maximum speed. And this result has been confirmed also by experimental tests. So here you can see the mean value of several experimental tests with different stiffnesses that we conducted in Pisa, and as you can see, the result has been confirmed also by experimental tests. And in this video you can see soft and stiff actuators in comparison in heating a nail. This test has been conducted with the cube you are using. And as you can see, the soft actuator can accomplish the task in 12 hits, while the same actuator with the higher stiffness can accomplish the task in 20 hits. So basically, that means that the mathematical translation of the problem has the characteristics that we wanted to embed in it, and it is meaningful for the maximizing impact task. Also, we tried with 2 degrees of freedom. You can see the comparison again between stiff and soft configuration of the robot. In this case, it can be proved also in the multiple degree of freedom case that the control is bang-bang-like. We are going to see it. Then for the switching instance, in this case, we have optimized the switching instance experimentally by trials. So we optimized them for the stiff case and for the soft case. Okay, so now let's see what happens if we switch from the series elastic case to the variable stiffness case. For the variable stiffness case, we studied the model in which we assume to control the position of the motor and the stiffness of the actuator. So this is the dynamic of the system, and this is the control vector that now has 2 components. again, this system is simple enough. We were able to derive analytical solution following the same classical path. These are the optimal control laws for the position, and for the position, basically, it is the same that we saw for the series elastic case and for the stiffness. So, first interesting thing is that also for the stiffness, the optimal control law is bang-bang-like. So the optimal way to change the stiffness in a task like this one is switches it from the minimum to the maximum value. And the switching function here depends on the product of a co-state and the difference between the control and the position of the actuator. That is basically the deflection of the elastic transmission. Okay, here there are all the passages we followed to derive the analytical solution that are a little bit tricky. So from the optimal control laws we saw in the previous slide, and from the initial conditions we were able to derive that the optimal stiffness at the beginning of the task has to be the highest the highest possible. So basically, since we have limits, has to be the maximum one. Then once we derived the conditions at the beginning of the task by the integration of both the state and the constate dynamics, that for this simple case can be done analytically, we can derive the first switching time, that is the time in which just the stiffness switches. Then we can see that the switches, that there is a structure in the switching instance. So basically what we can do is to prove which is the switching structure. And here, as you can see, the switching structure is first a switching in which just the stiffness changing, that is called here S with 2, and then a switches in which both stiffness and equilibrium position change. As you can see here from the switching functions, lambda with 2 appears both in the position control law and in the stiffness control law. So it's not a surprise that there is a switching time in which both stiffness and equilibrium position changes from a value to the other one. Okay, then from the terminal conditions, in this case the terminal constraint, and again the optimal control laws, we can derive the optimal controls at the end of the task, that in this case are again maximum. Summing up for the stiffness, we have this law, that is the optimal control law we can apply to this dynamical system to optimize the maximum speed. And the optimal control law says that if the system is in a speed-up phase, we have to use maximum stiffness, while if the system is in a slow-down phase, we should use a low value of the stiffness. So in order to visualize the result we have, we prepared we prepared these slides that represent all the tasks. So here we are at the beginning. So we have to move the reference, the equilibrium position, and during this phase, we have to use a nice stiffness value. Then when the stiffness, when the hammer reaches the reference, so basically when the hammer is overcoming the reference, we have to switch the stiffness from high value to the low value. Why? In order to be able to have the maximum potential energy stored into the elastic transmission. Then, when the spring has been totally loaded, we have to switch the reference, so basically the equilibrium position, again, and also the stiffness from low to high in order to maximize the effect of the impact at the end. It's interesting also in this case, since we have a complete analytical solution, derive the value of the velocity. Basically, in this case, we have the ratio of the variable stiffness maximum velocity with respect to the series elastic maximum velocity, and as you can see, this ratio depends on the ratio of the stiffness bounds that we have in the variable stiffness case. So, if these two stiffness values are the same, so basically if we are in the series elastic case, this ratio of course is 1. And it increases as the difference of the two stiffness bounds increases. And here there is the plot of the optimal control policies for the reference position and for the stiffness. As you can see, here there is the first stiffness switching that appears, as you remember, when the hammer overcomes the reference. And then here there is the simultaneous switching of both stiffness and equilibrium position that happens when the spring has been totally extended. Okay, here there are experimental results for two different inertia values, because of course, as in the other case, also in this case, the results of this model are valid for a proper dynamics of the system. And in this case, for a proper inertia, we found a further 30% improvement of the performance, so of the maximum speed, with respect to the series elastic case. Here are the values of the. Okay, so the problem we saw. Come? Yeah, please. Here?
Yes, for an experimental method, you show us a video that hammer hit the nail. But you show also a video that the hammer hit a nail. But I don't see any diagram or figure that shows the torque that you consume. How much torque? Did you also optimize the torque that affect the motor or not?
No, basically, in this case, the torque is as much as you can generate. So.
Okay, another question. In the optimal control, there are also two ways. Okay, one of them for input and one of them for the state. And how do you find the weighting for your optimal control or the other words? Do you use linear control, linear optimal control, or non-linear optimal control?
No, non-linear optimal control theory. So basically, for driving this, we don't do any hypothesis on the optimal control. So we don't do the hypothesis that the optimal control is linear in the state. As you can see here, is not linear in the state, and also the acceleration is not even a state. And basically, we were able to derive this solution just because at the end we have complete analytical solution for the state and the costates. And so basically we can, in this, if you substitute in these laws the solution for the states, for the control U with 1 and for the costate lambda with 2, you can find this law.
So in your
Okay.
controller, you consider full feedback stages to have feedback from all your states.
No. This is open loop optimal control. Okay, so this comes from, I mean, in principle, at the beginning of the process, we didn't do any hypothesis on the structure of the control. So the solutions, at the beginning, the solution can be dependent on the model, and that's it, or just on the constates, or just on the states. And this is, so this result has been found just at the end of the process. So we didn't do any hypothesis on the structure of the controller at the beginning. Okay, so the problem we have seen before has been solved without a constraint on the terminal time. So basically, the solution of the problem has an intrinsically optimal terminal time for accomplish the task. But in some cases, the terminal time is given, so basically we have to accomplish the task in a certain time, not after, not before. So it could be interesting to solve the problem also if the terminal time is given. For example, here you can see a first time kick, and in a case like this one, if you perform the kick one instant before or after, you cannot catch the ball. So let's see what happens if the terminal time is given. Let's jump to the results. Here we have a plot that is similar to the one we saw in the previous cases. And in this plot, the purple lines represent the user terminal time curves. Basically, that means that this line represents the task in which the terminal time is 2.1 seconds. Okay? This line represents the time in which the terminal time is 1.3 seconds. In the x-axis, we have, again, the natural frequency of the system, and in the y-axis, we have, again, the maximum speed that the system can reach. As you can see, the top points of all these lines build the lines that we saw before. So basically, the lines without constraints on the terminal time. And in this case, we have another important result, that is that based on the terminal time, there is an optimal stiffness value. So the optimal stiffness, constant stiffness, doesn't depend just on the characteristic of the system. So basically, in the previous case, we have seen that the maximum acceleration, velocity, and position ranges can influence the choice of the optimal stiffness. In this case, we can see that also the terminal time influences the choice of the stiffness of the of the transmission. And also in this case, of course, we have that these lines have been obtained with the case in which the control is the acceleration of the motor, and we considered also constraints on position and velocity. And here we have an experimental result for a given terminal time and 3 different stiffness value. And as we can see, the performance improves if we choose the correct stiffness for the system. Then we were able to solve also the variable stiffness case. And what we saw is that if the terminal time is given, the optimal control policy changes in this way. So the first switching remains at the same time, and the second switching is somehow anticipated in order to catch the terminal position constraint at the desired terminal time. Okay? That means, of course, that it's likely there is a terminal time under which is not advisable anymore to change the stiffness, and that's actually true. And since everything is analytically solved in this case, we derived also a value for this terminal time threshold, let's say, So if the given terminal time is larger than this threshold value, so it's better to change stiffness during the task. The other way around, if the terminal time is lower than this value, so the constant stiffness case is better. Okay. So now we are going to see again the max speed problem for a different kind of actuators, and in cases in which the problems are and the models are more realistic, and of course the complication is increased. So basically we will lose analytical solutions, and we will see that in some cases we can use and take advantage of the convex optimization theory that doesn't provide analytical solutions, still provides reliable and efficient solutions. That is, for example, the case of the maximum speed problem for the variable damping actuator that has been developed at the Italian Institute of Technology. And here we can see the model of the variable damping actuator. That is an actuator in which the motor side is connected to the link side through an elastic transmission with a constant stiffness, and between the motor and the link there is a clutch. There is a clutch, the torque of which is controllable. Okay, this is the dynamics of the system, and this is the external torque. This is the torque of the clutch, and this is the torque of the motor. Okay, for studying this problem, we take into account the full model, so without simplifications. And from an optimal control analysis, we saw the first interesting thing that is that again, the control of the optimal control law for the clutch, the torque of the clutch is Benben-like. In this case, that means that the actuator, the optimal way to use this actuator in this case, so for maximizing the link speed, is to use it or like a series elastic actuator or like a rigid actuator. Because if you think to the behavior of the clutch, when the clutch is used with its maximum torque, it means that the motor and the link are moving together. That is basically the behavior of a rigid actuator. And when you are using the clutch with its minimum torque, that means that the motor side and the link side are decoupled, and the elastic transmission comes into play. So basically, in this way, the actuator behaves like a series elastic actuator. So basically, we built several problems with different connections of the dynamics of rigid and series elastic actuators, and a proper way to do the transition between rigid and elastic, and the other way around. And then we can recast the optimal control problem into a convex optimization problem, in which The control variables are the, of course, the problems has to be discretized, and the control variables are the parts of the torque of the motor, and so basically we are trying to optimize here the motor torque behavior for accomplish the task. And the constraints are basically what the same constraints we have already seen, so bounds on the control, terminal the terminal state, some terminal states are specified, and limits on the speed of the motor. Okay, here we have the plot that basically sums up the results of this study, and we can see which advantages can give a variable damping transmission if we want to maximize the speed of the actuator. Here we have a plot in which where we can see the maximum velocity against the terminal time. The black line represents the performance of the rigid actuator, and the red dashed line represents the performance of the series elastic actuator, while the blue line represents the performance of the variable damping actuator with the optimal control policy. As we can see, if the terminal time is very limited, is very small, it makes sense that it's convenient to be rigid. So we can see that the rigid actuator behaves better. But if we have a variable damping actuator, we can make it behaves like a rigid actuator. So in this case, we don't lose, basically we lose very little amount of performance. The other way around, if the terminal time is high, so in this case, basically the actuator has all the time it requires to fully load the spring, and then to maximize the speed. So the best behavior is to use it like a series elastic actuator, and also in this case, if we detach completely the motor side and the link side, we can have this behavior and don't lose performance. While in the range in which the terminal time is in between these two values, with the variable damping actuator, if properly controlled, of course, we can reach performances that are better of what the rigid and the series elastic case. So that's what we gain in terms of performance with variable damping actuator. Okay, now we will see another task in which there are more constraints, and in which the goal is maximize the jumping height. We are going to see the results of this analysis for both the series elastic and the for both the series elastic and the parallel elastic actuation. In the series elastic, the spring is in between the motor and the link, and in the parallel elastic actuation, the elastic transmission is in parallel with the motor action. Okay, here we can see that after a little effort, the problem of maximize the jumping height can be reduced into a problem in which we want to maximize the velocity of the link side at the instant in which the system leaves the ground. Also, in this case, we take into account the complete model of the actuator. Here, there are the inequalities and the equations that we use to model the contact constraint. So basically that means that the vertical force has to be larger than 0 during the stance phase, and that the contact force has to be 0 at the terminal instant, that is the takeoff instant. Also, in this case, we take into account the bilinear characteristic of the motor. So basically, with this constraint, we relate the torque that the motor can generate to its velocity. And now we are going to see in a while what does it mean. Also, of course, we don't want that the upper mass of the system touches the ground during the loading phase of the task. Okay, here, as I told, we have the plot of one of a typical result. We can see the velocity of the motor against its torque. And as you can see here, there are the bounds. Okay, so in a certain region, the bounds of the torque and the speed is linear. Okay, that is one of the simplest models that we can take into account to model the proper behavior of a motor. Still is better than nothing. And as you can see, at the end of the task, that bound comes into play, and the solution is exactly on the bound. That means that here the torque is limited by the maximum speed that the motor can reach. Also, in this case, as in the previous one, the stiffness that maximizes the performance of the system depends among the other on the terminal time. And if the terminal time is low, the best stiffness is quite high, then it starts decreasing as the terminal time increases, both for the parallel elastic system and for the series elastic system. Okay, now let's see how to apply this idea to a 2 degrees of freedom robotic arm. In this case, to a series elastic 2 degrees of freedom, 2 degrees of freedom arm. The problem here is to maximize the velocity of the end effector. Okay, so no more the velocity of one joint, but the velocity of the end effector in a given direction. So basically, you can imagine the task to hit a ball and to hit a ball with the maximum speed, and also you want to send the ball in a certain direction. In this case, we used a model in which we assumed to control the velocity of the motors, and we found a solution basically in 2 steps. One offline step in which we built a rough map that connects the switching instance of the controls. Also, in this case, we can show that the control is, for the velocity of the motors, is bang-bang-like, so it switches from the minimum to the maximum. And so basically, in the first step, what we need to find are the optimal switching instant in which we have to change the velocity of the motor. So in the first step of the solution, we built an offline map between the switching instance and the final position of the arm and the terminal time of the task. Then online, once we know the position of the arm and the terminal time, online we perform a local optimization around the best solution of the offline map. And then we control the robot through a model predictive control algorithm. Okay. So basically here you can see a simulation that shows how should be performed the task. This represents the goal, and this is the ball that has to be sent towards the goal. Okay, so as I told you, the experimental tests were conducted combining the 2-stage optimization approach we saw before with a nonlinear model predictive control algorithm to control in real time the robot. And if it starts, okay. So that's the result, and the distance between here and there is between the start position of the ball and the goal is 1 meter, and the width of the target is 10 centimeters, and the diameter of the ball is 4 centimeters. So it's quite good as results. And one thing I have to let's say admit or to say is that it works since you have a carefully identified model of the system. Since the control is model-based and also the optimization is model-based, you need to have a carefully identified model of the system. Then once you have it, it works pretty good.
Question. And the optimal solution depends on what from the model? So I guess you're
In this case, we exactly don't know on which, I mean, since we cannot solve this problem analytically, we don't know how the analytical solution depends on the states and on the model. So what we have is basically we have this map that gives us the solution, the optimal control solution to apply to the system, but we exactly don't know on which part of the model it.
I thought here, I saw that you use nonlinear accuracy, which requires the analytical model that you have, right?
Yeah. Yeah, I mean, we have the analytical model of the system, but we don't know the optimal solution since we use the we derive numerically the optimal solution. We don't know exactly on which part of the model it depends more and on which part it depends less.
Did you publish this, or is it just ongoing research?
No, it's ongoing research. So basically, it's finished the work, but we have to write the paper. Okay. So, summing up for the max speed problem, we saw that optimal control gives us insight on physical properties and behaviors of the system. So first of all, there exists a constant stiffness that maximizes the performance of the systems, and we saw that at different levels from the simplest system to quite complex system to systems that takes into account also realistic models of the models. And that optimal stiffness value depends on the parameters both of the task and of the system. And this constitutes per se a motivation to go towards variable stiffness mechanism, variable stiffness actuation that from this point of view can allow to tune the parameters of the system in order to maximize the performances given the parameters of the task and of the models. Moreover, through a careful analysis of the results that we can get from optimal control theory, we can learn lessons in order to understand how to manage the additional degrees of freedom that soft robots have. In this case, in the max speed problem case, the lesson we learned is stiff when speed up and soft when slow down. Okay, so now let's see, quickly see, because I really wanted to finish in an hour, I'm sorry, because I wanted to let you work on the demonstration, but okay, I will try to be as quick as possible. So another problem is what is the role? What is the importance of having soft robots of having soft elements if we want to minimize the energy consumption? So the idea is to optimize the following actuation parameters: the stiffness for the series elastic case, and the stiffness and the preload of the springs in the parallel elastic actuation case, that minimizes the squared power or the squared torque cost index. You can think as an example to the, of course, pick and place task. Okay, let's see how can appear the problem formulation. So the index we used in this study case is the, as I told, R2. One is the squared power, and one is the squared torque. Of course, there is this sum. That means that we want to minimize the sum of the power or torque of all the actuators of the system. And so now let's see the constraint. Here it is the dynamics of the system. In this case, we consider the full nonlinear dynamics of the system. The fact that the motion is cyclic, other possible constraints, equalities and inequalities constraints, and bounds on the optimization variables that are the parameters of the actuators. In the most general case, of course, this problem, the solution of this problem depends on the trajectory, on the desired trajectory, and on the actuation parameters. But if the stiffness matrix is diagonal, that means that there is no cross coupling between motors and joints and links. So if this hypothesis holds, the problem can be decoupled. So basically, once the optimal trajectory or a trajectory is given, then the stiffness and the stiffness in the series elastic case, or the stiffness and the preload in the parallel elastic case, can be easily optimized. Or the other way around, we can have a function that gives the optimal stiffness that depends on the trajectory. Then we can substitute this function into the problem formulation and then optimize the trajectory. Here, in this table, we can see the solution of the stiffness and the preload for the two indexes, in which these capital letters represent integrals of the dynamics of the systems, of parts of the dynamics of the system. But once the trajectory is given, these parts can be analytically evaluated. Okay. Here we can see a typical trend of the cost function against the stiffness. In this case, the stiffness of one joint of a 2 degrees of freedom manipulator that performs a pick and place task. Okay, and here we can see experimental measurements of the current of the manipulator that performs the pick and place task. The red line represents the the rigid manipulator, so the manipulator in rigid configuration. The optimal, this line represents the manipulator with the optimal stiffnesses at each joint. And this blue dotted line represents the manipulator with the softer springs. We had this green line with an intermediate case. So basically, we can see that actually if we can optimize the springs at the actuation, we can indeed minimize the energy consumption during the task. Okay, then here there are first simulation studies in which we are trying to optimize both trajectory and actuation parameters. Okay. So now let's see for the robustness point of view, the task in which we want to minimize tracking error for example, in force tracking under a robustness constraint. So, in the literature for the force control and with soft robots, this basically was the process. In the 80s, the mantra was the stiffer the better. So if you want to do force control, you need a stiff manipulator, as stiff as you can, and then you can get precise tracking, precise motion, precise control. Then in the 90s, basically with the work of Jerry Pratt that introduced the series elastic actuators, the robotics community starts to see that soft could be good, in the sense that with soft actuators, probably the performances in the control could be a little worse than with the rigid case, but there are other benefits, like for example the shock absorbance and the reduced transmissibility of an external disturbances through the transmission of the actuator. Then in the 2000s, for some cases, not yet for the force control, some studies started to show that with variable stiffness, some tasks could be performed better than with series elastic. So now let's see what can be done with force control. Okay, that is the work of the work by Pratt, basically. That ends with the facts that series elastic actuator has some benefits that are, for example, the capacity of store energy, and this benefit is exactly what we used in the max speed problem, and also in the minimization of the energy consumption during a cyclic task. And then series elastic actuation can improve the shock tolerances of the manipulator, of the robotic structure in general. So now let's see a little bit into the details. What does it mean? Here we have a model of a soft actuator with the environment 2, and we can consider two inputs. One is the actuation force, and the other one is the environment displacement. Actually, the actuation force is the real input of the system we have, and the environment displacement is a disturbance more than a need. And as output, we in this problem are considering the external force acting on the link side, and the transmission force that is acting on the transmission of the motor side. Okay, by the analysis of the norm 1 of the transfer functions between inputs and outputs, we can see that if we increase the stiffness of the transmission, what happens is that, of course, the control effects on the output are increased. So let's say the control authority increased. But also the effects of the disturbance on the outputs increased. So the question is again, is there an optimal stiffness to perform this task? So again, repeat the task. The task is to control, to regulate the external force of the actuator while taking the transmission force under a certain level. The optimal control problem here has been translated into a convex optimization problem. Basically, also in this case, we discretize the dynamics and since the dynamics is linear, basically the problem can be translated into a convex optimization problem with limits, as I told, on the transmission force and, of course, with control bounds on the force of the actuator can generate. And let's click the results. So here we have the plot that shows the performance index, that in this case is the error that we are having with respect to the desired value of the external force against the stiffness of the transmission. And as we can see, actually, is there a transmission stiffness value that minimizes the error we have in the tracking of a desired external force at the link side. Moreover, we performed several simulations and saw that the optimal value of the stiffness depends on the parameters of the model, of course, also in this case. And an interesting thing in this case is that the optimal stiffness depends on the environmental stiffness and decreases with the environmental stiffness. Okay, 1 hour and a half. So if you have questions, or if not, we can thank you for your attention, and we can switch to the hands-on.